For a cis isomer, it can be possible that there is no asymmetric center, but only for a cis isomer. We can do this by evaluating the image as we move, well, for some trans isomers as well. We can do this by evaluating the image, as I said, by going clockwise from an asymmetric center all the way around and counterclockwise and evaluating it. So if we go clockwise, we would have, going from this asymmetric center clockwise, we have Ch2, followed by Ch bonded to substituent Ch3, and I'm going to go ahead and put that as a solid wedge, then bonded to a Ch2 before we get back to the asymmetric center. If we go counterclockwise, we get the exact same answer. Ch2 bonded to Ch, which has a solid wedge to Ch3, bonded to Ch2. Because they look the same as you go clockwise and counterclockwise from the asymmetric center, they have an internal mirror plane and are achiral. No asymmetric center is present. They do not have an enantiomer. The mirror image is superimposable. If we look at the trans isomer, we would get the same thing going around the ring in both directions. There are only two stereoisomers here, cis and trans. No enantiomers, no diastereomers. Furthermore, when we have no asymmetric center, one of the things that I would like to point out is that we have an internal mirror plane, just like we looked at in the handout. If we cut the atom in the way that, if we cut the molecule across the line that I have shown, the two halves are identical. So there is an internal mirror plane, and as we learned in lab, when we have an internal mirror plane, the molecule has a superimposable mirror image and is achiral, does not have an asymmetric center. Okay, looking at this cis isomers, I can see a line of symmetry that bisects the atom and the ring. It has an internal mirror plane. It does not have asymmetric centers. We can also look at this going clockwise and counterclockwise. Choose one of the two possible asymmetric centers and go around the ring, identifying the groups. If they are the same in whether you go clockwise and counterclockwise, then they are not asymmetric centers. Starting from the bromine, we would have Ch2, Ch2, CH, solid wedge Ch3, bonded to CH2 and CH2. If we go counterclockwise, we have CH2, CH2, CH bonded to solid wedge, CH3. Then we have CH2 and CH2. If you want me to be more clear, I can use a highlighter and highlight each one a different color. While the carbons are physically different, when you start clockwise, they're identical to the order in which the groups appear in the other direction. The yellow CH2 is the same group as the purple CH2. The orange CH2 is the same group as a blue CH2. They have the same identity. So because the groups appear with in the same order with the same identity, the two groups are identical, and there is no asymmetric center. Okay, so those are cis stereoisomers. If the groups are the same as you go clockwise, or as they are when you go counterclockwise, they have the same identity, then there's no asymmetric center. And then a shortcut, if you're able to see them clearly, is that if there is an internal mirror plane of symmetry, such as bisecting in two, then there is no asymmetric center. Two asymmetric centers, three stereoisomers. It is possible that we can have an internal mirror plane of symmetry when we have two asymmetric centers in a non-ring molecule. So here we have two asymmetric center molecule that has three stereoisomers instead of four stereoisomers, such that the 2 to the n rule does not apply. So how does this happen? We have 2,3-dibromobutane. We show the perspective drawing of 2,3-dibromobutane and the Fisher projections of the stereoisomers. Molecule 1 does not have an asymmetric center, but it is still a stereoisomer. It simply does not have a pair of enantiomers. And that is because there is an internal mirror plane of symmetry that I am showing with this black line. The top half of the molecule is identical to the bottom half of the molecule. When the asymmetric centers, which I will highlight yellow, yellow, and green, have the same groups, at least one of the stereoisomers will be achiral and have an internal mirror plane. So if you look at the yellow carbon, the four groups that we have in the order of priority are bromine is highest, followed by the second group, which is a CH carbon bonded to bromine and methyl. Then the third priority group is the methyl group, and the fourth priority group is hydrogen. If you look at the second asymmetric center, highlighted in green, the groups in the order of priority for the green are bromine highest. That is really irritating that it keeps erasing that. Green. What do they think? I'm not serious? Okay, bromine first, followed by the yellow asymmetric carbon, which is a CH carbon that is bonded to bromine and methyl. Then we have the methyl group and the hydrogen. Notice that both carbons have the same 4 groups. This means that if they are arranged in such a way that they created a mirror plane in the molecule through the order of arrangement, then there are no asymmetric centers, and the molecule is called achiral. And for this specific molecule, it's odd because we know that the yellow carbon has 4 different groups. So it has an asymmetric center. The green carbon has 4 different groups. It has an asymmetric center. So how can it not be chiral? It's not chiral because of the mirror plane. It does not have an enantiomer. The enantiomer, if you build the mirror image molecules, they will be superimposable because of the mirror plane. We call this type of molecule a special name. It is the Meso molecule. Meso. A Meso molecule is a stereoisomer that has asymmetric centers, but that is achiral because of an internal mirror plane. If you look at molecule 2 and 3 in the Fisher projection, they do not have an internal mirror plane because the bromines are on opposite sides. These molecules are enantiomers, and their only diastereomer is the Meso molecule. A Meso compound has asymmetric centers, but is optically inactive because it has a superimposable mirror image. And the reason that it has a superimposable mirror image is that it has an internal mirror plane of symmetry. This is only possible when both asymmetric centers have the same 4 groups. A Meso compound has a plane of symmetry, as I said, and both asymmetric centers are bonded to the same 4 groups. So here we say a compound with 2 asymmetric centers, Meso, a compound with 2 asymmetric centers that has the same 4 groups bonded to each asymmetric center. And this, okay, so any molecule that has 2 asymmetric centers with the same 4 groups bonded to both asymmetric centers will only have 3 stereoisomers, a Meso compound and a pair of enantiomers, so that the 2N rule will not apply. Let's make a note of that. 2 to the N rule does not apply. It is not valid in this case. When two asymmetric centers have the four same groups, then the 2 to the n rule fails. Meso compounds. For cyclic compounds with the same substituents bonded to two asymmetric centers, the cis molecule will be a meso compound and the trans molecule will be a pair of enantiomers. Notice that this is true when we actually have asymmetric centers. These molecules, the trans molecule does not have an internal mirror plane of symmetry. The trans molecule does not have an internal mirror plane of symmetry, and both of them do have asymmetric centers, because if you write out what occurs as you move from clockwise to counterclockwise, for this carbon, for example, we encounter CH2, CH2, CH, solid wedge, CH3, followed by CH2. If we move counterclockwise from the same carbon, we encounter CH2, and I'm going to stop as soon as I encounter a different. So that's the same at the first group. Then the second group is CH, solid wedge, CH3. And there I encounter my first difference. Moving clockwise versus counterclockwise is different, and therefore the carbon circled in orange is an asymmetric center. The other carbon is also an asymmetric center. So carbon 1 and 3 on dimethylcyclopentane are asymmetric centers. You will find the same is true of the trans. These are asymmetric centers. On the cis molecule, there is a plane of symmetry because the cis, if you cut it in half, since the solid wedges are the same, it has a mirror plane. It's a meso compound. But for the trans, if you cut it in half, there is no mirror plane because the solid wedge is not equal to the hatched wedge. Therefore, it has two asymmetric centers and zero internal mirror planes. It has a non-superimposable mirror image and enantiomer. Naming of stereoisomers. When we have two asymmetric centers, you have to identify the configuration of both asymmetric centers as either S or R and include both in the naming of the molecule. When you name the molecule for its asymmetric centers, you will begin the name of the molecule with the location and configuration of the stereocenter at the beginning in parentheses. So for the molecule shown here, we have an S carbon and an R carbon. And just for fun, we're going to draw the rotated form of the R carbon since hydrogen is on the solid wedge. If I rotate it about this methyl group in black, holding that methyl group steady, when I rotate the hydrogen back, then what will occur is that the methyl group will go to the solid wedge. The carbon, that's incorrect. We're not moving the methyl group. I apologize. Okay, the methyl group will stay where it is because that is the axis around which we are rotating. The carbon bonded to the hydroxyl group, carbon numbered as number 2 in the numbering, or group 2 in priority of the numbering, will be on the solid wedge when I rotate. So I will get C. Let's just do the colors. Okay, so yellow, whoops. Darn it. I need the highlighter. Okay, I'm just gonna go with colors. Yellow, the yellow carbon, blue methyl. We're gonna go with a green hydrogen and an orange bromine. Okay, so if I draw my, whoops, go back to the pen. Yes, okay, so the pen, no, eraser, different colors. Okay, dash, dash, dash on the hatched wedge after the rotation will be the hydrogen in green. Green. It's not the highlighter. Oh well. Okay, green. The green hydrogen. Then on this solid wedge that comes up from the other side, where previously the yellow carbon was, after the rotation, I thought I changed the color. I really did. After the rotation, that will be the orange bromine. Then we can label the priorities of the groups again. So bromine is 1, yellow carbon is 2, blue methyl is 3, and hydrogen is 4. Now, the lowest priority group is on the hatched wedge. When we draw the line from 1 to 2 and from 2 to 3, we are moving clockwise, and we know it is the R configuration. So, then we have to, you also have to remember to number the carbon for naming. The terminal carbon that is closest to the OH group is going to have the lowest possible number. So this is a 4-carbon molecule. 1, 2, 3, 4 carbons total. Carbon 2 is either bonded to the hydroxyl group or to the bromine. Since hydroxyl has to have the lowest possible number, we make carbon 2 bonded to the hydroxyl group. I'm going to number these using the color purple. So carbon 1, carbon 2, carbon 3 bonded to bromine, and carbon 4, the last methyl group. This is a butanol. It's a 2-butanol because the alcohol is at carbon 2. The substituent is bromine. So this is 3-bromo-2-butanol. And after we identify the configuration of asymmetric carbon 2 and asymmetric carbon 3, then we can complete the name as 2 parentheses 2s, comma 3r, close parentheses, dash 3-bromo dash 2 dash butanol.